Hello, welcome. This is a demonstration of a open source project called TetraHelix, which is a mathematical investigation of the Burdick-Coxeter tetrahelix. What you're seeing right now is a three-dimensional rendering of the Burdick-Coxeter tetrahelix. As you can see, it's just a series of regular tetrahedra stacked together, which have the interesting property that they make a helical column. What I have done is to develop a continuum which allows this helix to be designed or twisted and untwisted. So by using these sliders here, we can change the pitch of the tetrahelix to make it longer. Eventually, if we drive the so-called rail angle to 0, we create a regular beam called the equitetra beam, which has a cross-sectional area of an equilateral triangle. As you can see here at the top of the screen, perhaps you can see here, the min-max ratio of the longest member in the system to the shortest member in the system is printed and changes as I change the rail angle. In fact, going all the way back to the regular Burdick-Coxeter helix, you'll see that it's almost regular to within numerical error. That is, all the links are exactly the same. What has been developed is a continuum of optimal untwistings that minimize the ratio of the maximum length to the minimum length, and it's being shown here. It also computes a number of other things. The surprising result, which I've written up in an academic paper, is that this is accomplished by changing only the so-called two-hop, or the longest edge in the system. So even when it's completely untwisted, as it is here, the one-hop edges do not change, and the rail edges are always the same length, in this case half a meter. But we can change the two-hop length, and by changing only that, we can move through all of these twistings. Since we're printing the pitch, for example, which happens to be irrational in the Burdick-Coxeter helix, we can actually design a pitch using these sliders to try to match for example, an integral pitch instead. So I can come close to getting an integral pitch in terms of meters per revolution. That would allow an architect, for example, to design this column to have exactly the revolution that they desired within certain limits. It's also the case that we can change the chirality of the system. All of the tetrahelices in this continuum are either counterclockwise or clockwise in a right-handed system, and we can change that. We can also change the radius, for example, or change the basic rail edge, which makes the whole system bigger when we have the system in the optimal mode, so that we're guaranteed to get optimal tetrahelices in the sense of the minimum maximum to min length. If we click to make this free, then we can change parameters and we're not necessarily optimal anymore. For example, here is a rather attractive, elegant lengthening, which is no longer optimal in terms of the ratio. In fact, the longest members are 83% larger than the shortest. We can go back that way, and we could make the radius actually higher to make a sort of a stubby tetrahelix like this, which might be interesting for some other purpose, like, for example, providing a larger end radius so that something could fill the object, like a pipe or ladder for a human being, or to resist buckling forces if this system were under compression. So all of this is open source. The particular mathematics are within a single given file, which you can easily find. Here is the main file tetrahelix_math.js, which represents the actual mathematics necessary to do this. It uses the browserify system to bundle it into something which can be used by the browser so that it can also be tested with Mocha using automated test. It's all in the repo pub/in/tetrahelix. The rest is the three-dimensional rendering stuff, which has very little to do with the mathematics. And down here you can see that as I change each thing, I'm recording all of these just for the purpose of experimentation so that you can investigate how various changes affect the in radius, the pitch, the length, or the min-max ratio, so that this page becomes an interactive design tool for tetrahelices, which are slightly irregular. Thank you.